Hey guys, today we're going to be looking at the definition of a derivative. We're going to start with a little bit of review of our average rate of change though. So we need to find the average rate of change of the function f of x on the interval -2, 0. And then it says sketch the function in the secant line that represents this average rate of change. So I've already sketched them over here. We've got this parabola that's shifted down 1. And then I've got my secant line here that's going to go through my points -2 and 0. So I'm looking at f of 0 minus f of -2 over 0 minus a -2 gives me +2. So on the top, f of 0 is -1 minus f of -2 is a +1 over 2. So that's going to give me -2 over 2, which is equal to -1. So my average rate of change right there is -1. And now we're going to find the average rate of change of the function with our interval x to x plus h. So that means I'm looking at f of x plus h minus f of x over x plus h minus x. So remember those x's cancel out. So I'm looking at the f of x plus h minus f of x all over h. So that means I'm looking at 1/2 x plus h squared minus 1 minus my 1/2 x squared minus 1, and that's all over h. So we need to multiply out our x plus h squared. So that's going to give me a 1/2 x squared plus 2xh plus h squared minus 1, and I'm going to go ahead and distribute my negative here. So minus 1/2 x squared plus 1. So my -1 and +1 cancel out, and that's all over h. So when I distribute my 1/2, I'm going to have a 1/2 x squared plus xh plus 1/2 h squared minus my 1/2 x squared all over h. And my +1/2 x squared and -1/2 x squared cancel out. So that gives me an xh plus 1/2 h squared over h. And I'm going to factor out an h, and that's going to give me an x plus 1/2 h all over h. So I end up with x plus 1/2 h. So remember that when we are talking about our average rate of change, we need 2 points because we're using that slope formula. So how can we use the average rate of change formula to find the rate of change at 1 point, which is our instantaneous rate of change? And so I've got a nice little visual here. Let me open that up for you guys. So if we're looking at that visual right here, what we're doing is we're trying to take a secant line and turn it into a tangent line. So what I'm trying to do is move this point right here so that it's closer and closer to that point right there. So I'm moving the c plus h so that it gets closer and closer to c. So I'm taking my tangent or my secant line and I'm trying to make it into a tangent line, so where they're the same point. So that's kind of a visual representation of what we are looking at. So what we're doing is we're trying to make it so that c is equal to c plus h. So we're trying to make it so that h is equal to 0. So what I'm going to do is I'm going to take the limit as h goes to 0 of my f of x plus h minus f of x all over h. So that's the average rate of change formula. And we're getting h to go to 0. So once again, if we look at our little visual right here, we're trying to make this get closer and closer and closer and closer and closer to this point. So it's kind of taking the limit, moving it closer to here. So this is our formula that forces the average rate of change to become an instantaneous rate of change. And this right here is called the definition of a derivative. So a derivative is a common word used to mean the instantaneous rate of change. And there are a couple different ways that we represent the derivative of a function. You can use f prime of x, so that's with that little apostrophe right there. You could use y prime, which is the derivative of y, or dy over dx, or dy dx, which is the derivative of y with respect to x. So right here is kind of how you say all of those, and the first one is what it means. And so the ones that are most common are this f prime of x and dy dx. So those are the ones that I'm going to use the most. So we're going to go back to that first example with our 1/2 x squared minus 1. We're looking at our same graph. And so this time it says we're going to sketch the line that represents the instantaneous rate of change of the function at x equals -2. And we're going to look at how this line is different than the line drawn on number 1. So let me go ahead and draw my graphs here. So I've got a parabola that looks like this. I'm not great at drawing these on my tablet here because I can't actually see what I'm writing. So that one's not too bad. And I'm trying to find the instantaneous rate of change at -2 right here. So what that is going to be is that's going to be a tangent line that only touches my graph at that -2. Which my drawing is really bad, so it doesn't look like it only touches there, but that's the idea, is that it only touches at that one point right there. So this one is a tangent line. So this one only touches the graph at one point. Whereas our secant line, so if we come back and look at our example 1, it touched at 2 points. So that's the difference here that we're looking at. We're trying to get it so where it only touches at 1 point. And then is the derivative positive or negative at this point? Our derivative is going to be negative because that tangent line is going down. It's got a negative slope. So another way that you can think of a derivative is the slope of a tangent line. So remember, we were using our secant lines to find our average rate of change. And so that average rate of change is the slope of that secant line. So our derivative is going to be the slope of our tangent line. So find the instantaneous rate of change of the function on x to x plus h. So we're going to do the exact same thing we did in the last example over here, except for now we're just going to put a limit in front of it and use that limit to help us find our slope of our tangent line. So what I'm looking at here is the limit as h approaches 0 of f of x plus h minus f of x all over h. And I know from my first example 2 right here that when I simplify all that down, I get to x plus 1/2 h. So we're not going to do that whole process again. We can go ahead and just say that we're looking at the limit as h approaches 0 of my x plus 1/2 h. So what I'm looking at is x plus 1/2 times 0, or just x. So what that means is that any point that we have here, so at x equals -2, that means that our tangent line slope, which is equal to x, would end up giving us a -2. So the slope of this tangent line right here is -2. And so that's kind of what we're doing here. So now we're going to look at what these questions are going to look like on the AP test. So when you get to the AP test, you're going to end up with multiple choice questions that are going to kind of look like this. And so it's going to say if f of x is this function, then which of the following is equal to f prime of x, or our derivative of x? So that means that we're looking for the limit as h approaches 0 of f of x plus h minus f of x all over h. So I can go ahead and cross out C and D because they're talking about x approaching something. And so now we're looking at A versus B. And so you'll notice the difference here is I have 2 different square roots versus 1 square root. And so we are looking for f of x plus h minus f of x. So my f of x function is that square root of x plus 2. And so if I was looking for f of x plus h, that's going to be the square root of x plus h plus 2. So we are going to have two different square roots here. So our answer is going to be A. They should not be under one square root, two separate square roots. 6 follows the same pattern. So I can cross out C and D because they're talking about x approaching. And then I can also cross out B because I need to have the two different square roots. My f of x function is that square root of x minus 5. Another way that it may look, and these would end up being multiple choice if they were on the AP test, it says what function is the definition of the derivative being applied to in this limit? So remember our limit as h approaches 0 is f of x plus h minus f of x over h. So when it's asking what function this is being applied to, it's going to be whatever's after that subtraction sign on the top of our fraction. So for 7, it's going to be this 3x squared. So my answer for 7, I would say that f of x is equal to 3x squared. For number 8, it's going to be the x cubed. So I could say that f of x is equal to x cubed. It's whatever is after that subtraction sign there. So then for number 9, it would be the square root of 2x. So f of x is equal to the square root of 2x. So this is our definition of a derivative, the limit definition of a derivative. And there is another definition of a derivative that's used. This one is called the alternate form of the derivative. And this one applies when you're looking at a specific x value. So this one is that the limit as x approaches c of f of x minus f of c over x minus c. So that's kind of the same idea using our visual representation. Let's say that this point right here is our x, and this point right here is our c, or this point right here is our x, and that point's our c. And I'm trying to take this point here, this c plus h, or in this definition case, it's just the x, and I'm trying to get it closer and closer to c. So it's approaching that c value. And so this is kind of the same thing, but this time we're looking at a specific function value. So a specific x value that we're plugging into this. So 10 says apply this alternate form of the derivative to find the derivative for f prime of x at x equals negative 2. For our function f of x is equal to 3x squared minus 1. So the limit as x approaches c of f of x minus f of c over x minus c means that I'm going to look at the limit as x approaches, well, my c in this case is going to be negative 2 for f of x minus f of negative 2 over x minus my negative 2. So I'm looking at the limit as x approaches negative 2 of 3x squared minus 1 minus 3 times a negative 2 squared minus 1 all over, and on that bottom right there, I'm going to change that to x plus 2. Minus the negative gives me that plus 2. So let's clean this up a little bit. I'm looking for the limit as x approaches negative 2 of 3x squared minus 1 minus, well, negative 2 squared gives me a positive 4 times 3 gives me a 12 minus 1 is going to give me 11 all over x plus 2. So the limit as x approaches negative 2 of 3x squared minus 12 over x plus 2. And you can notice here that if I plug in that negative 2, I'm going to get a negative 2 plus 2 in the bottom of my fraction, which would give me a 0. So on the top, it does the same thing, which is my indeterminate form. So I need to see if there's anything that I can factor out here. So I can take out a 3 on the top, so the limit as x approaches negative 2 of 3 times x squared minus 4 over x plus 2. And then that top also factors as a difference of 2 perfect squares. So 3 times x plus 2, x minus 2, all over x plus 2. The x plus 2's cancel out, so I'm looking for the limit as x approaches negative 2 of 3 times my x minus 2. Because I don't have a denominator anymore, I can plug it in. So I'm looking at 3 times a negative 2 minus 2, or 3 times a negative 4, which gives me a negative 12. And our last two problems say identify the function that this limit, so our alternate form, is being applied to. So remember that that limit is the limit as x approaches c of f of x minus f of c over x minus c. So I know that my c is 2, because that's what we're approaching right here. And so in this case, whatever function it is going to be what's in front of the subtraction sign. So this term is going to be my 2x cubed. So f of x is equal to 2x cubed. And I can check by plugging in 2. If I take my f of 2, that's going to give me 2 times 2 cubed, which is 2 times 8, which gives me 16, which matches with what I have in that second part of the numerator. And for number 12, it's going to be my sine x. It's that first part when we're looking at the alternate form. So in this case, I'm going to have that f of x is equal to sine x. And my c that I'm going to is my pi over 2. So if I plug that in, I look for f of pi over 2. That means I'm looking for sine of pi over 2, which gives me 1. And so that checks out with my fraction here. So this is kind of an introduction to the definition of a derivative. We are going to work on this more next class period. We're going to have a definition of a derivative part 2. For now, that's all we're going to do. And you have a homework assignment, 2.2 worksheet. And remember that we are trying out GoFormative right now to see if that works out for us. So make sure you do that assignment and GoFormative.